Okay, this morning we're going to look at molecular shapes, and then later on we can look at hybridization, and we can work out the molecular shape of a molecule by counting the number of electron domains around the central carbon atom, or central atom, sorry. And we look at this in more detail. This is what we're going to look at in this class. So we're going to predict the shapes of and bond angles in simple molecules and ions. And to do this, we're going to apply the VSEPR theory to include the following systems: trigonal, for example BF3, linear, such as BeCl2, tetrahedral, such as NH4 plus or CH4, pyramidal, for example H3O plus or CH3. I think that should be CH3 minus, in fact, and NH3. Non-linear, for example H2O, and octahedral, such as FS6. We'll in fact move on to the shapes of molecules such as ethene, and benzene, and apply the concept of hybridization in a later video. So, according to the valence shell electron pair repulsion theory, which is VSEPR, electron domains on a central atom of a molecule will repel each other, so they arrange themselves as far apart as possible. So what are electron domains? Electron domains are unbonded electron pairs, single, double, or triple bonds. So, for example, this molecule here has 4 electron domains. That's one of them, that's 2 of them, that's a third one, and that's a fourth one. And we can refer to the electron pairs as electron domains. In a double or triple bond, all electrons shared between these two atoms are the same on same side of the central atom. Therefore, they count as one electron domain. So all electrons are shared between these two atoms on the same side of it. So this, in other words, is one electron domain, although it's a double bond. So how many electron domains are there in CO2? Well, that's an electron domain, and that's an electron domain. So therefore, there are 2 electron domains altogether. What about in NH3? That's an electron domain. So is that, so is that, and so is that. So you have 4 electron domains. How many are bonding? 3 of them. How many non-bonding? 1. So this has 3 bonding domains and 1 non-bonding. What about SF6? Well, in this case, you have 1, 2, 3, 4, 5, 6 electron domains, but you're only dealing with the central atom. And the number of electron domains determines the shape of the molecule. If you have 2 electron domains, you're going to be linear. If you have 3 electron domains and there's no lone pairs, then you're trigonal planar. If you have 2 electron domains and 1 lone pair, you have a bent shape. If you have 4 electron domains and all of them are bonding, so there's no non-bonding pairs, you have a tetrahedral shape. If you have one lone pair and 3 bonding pairs, you have a trigonal pyramidal shape. And if you have 2 lone pairs, you have a bend shape. Although this shape is different from this. This bond angle is much less. This is a bond angle of 120 degrees, whereas this is about 105. We'll explain that later on. So if you have 5 electron domains, you have a trigonal bipyramidal shape. If you have 1 lone pair, you have what is called a sawhorse. If you have 2 lone pairs, you have a T-shape. And you have 3 lone pairs, you have a linear shape. Probably don't have to bother with these, but I don't think it's on the syllabus. So the syllabus had just these ones. So I probably don't have to worry about the 5, but learn them nonetheless. And then octahedral, if you have 6 electron pairs, octahedral. If you have 1 lone pair, you become a square pyramidal shape. If you have 2 lone pairs, you have a square planar shape. 3 lone pairs, you have a T-shape. And 4 lone pairs is linear. So in order to determine the number of electron domains, it is necessary to draw dot and cross diagrams, or for that matter, Lewis structures. Probably Lewis structures are easier. You can have hydrogen, chlorine, hydrogen chloride, and water, for example, or oxygen. You can see that in the water molecule, the oxygen atom contains 4 electron domains, 2 of which are bonding, and 2 of which are non-bonding. It has an electron pair geometry that is tetrahedral, and a molecular geometry that is bent. So this one here, tetrahedral, with a molecular geometry which is bent. And carbon dioxide has 2 electron domains and is therefore linear. And Lewis structures can be drawn rather than dot and cross diagrams. And we've looked at the NO3- before. So we know that nitrogen has 5 valence electrons, oxygen has 6. Therefore, there are 23 electrons around altogether. But there's an extra electron, because NO3- is a negative charge, and therefore 24 electrons in total. You put the N first, and then you put the oxygens around 2, 4, 6. You have 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, since each single bond accounts for 2 atoms, after completing all the oxygens, all electrons are accounted for. However, N is electron deficient, and thus a double bond is formed with oxygen. And that's why we get that. And that's the Lewis structure for NO3-. And therefore you have 3 electron domains altogether. And the shape is therefore a trigonal planar shape. That should have been planar, not plane. Hold on. See if we can adjust that. Yeah, okay. It is necessary to determine the formal charges of the atom, and this can be done as follows. The formal charge of an atom is the number of valence electrons in the neutral atom minus all shared electrons plus or 1/2 of all shared electrons. So if you look at nitrogen, NH2, for example, Nitrogen has 5 electrons altogether. And then you have one of these, and one of these, that's 2. And then you have 4, 6. That's 6 electrons. So therefore, the charge of the nitrogen will be -1. In this case, for the nitrate ion, we can see the formal charge is valence electrons minus non-bonding electrons. And this one you have on that altogether, and bonding electrons divided by 2. So for nitrogen here you have 5 electrons altogether. And you have how many non-bonding electrons? None. Bonding electrons, 1, 2, 3, 4. So nitrogen is +1. This oxygen here, well, you have 6 valence electrons, minus half of these. That's 1, 2. That's half of the number of shared electrons is 4 altogether. 5 by 2, that's 2. Then all of these, 3, 4, 5, 6, have 6 minus 6, which is 0. But here, we're going to have 6 electrons from the oxygen, minus 6, and also -1. So it comes to -1 for this oxygen and this one. Oh Lord. So the in this case, the structure of the nitrate is that. Oh, hold on a second. So the point about formal charges is sometimes you'll have a structure where you can draw more than one possible structure. But the one which will form is the one with the lowest number of formal charges on the different atoms. So, for example, which structure of sulfate ion will contribute most to the electronic structure of the sulfate ion? And in order to work this out, we need to first of all work out all the possible structures for the sulfate ion, which is A, B, C, D, and D. Remember, all of these are possible because sulfur can hold more than 8 electrons in its outer shell. So, what's the oxidation state of the sulfur in the first one? Well, you have 6 minus 4, which have 1, 2, 4 bonds. 6 minus 4 is +2. And then each oxygen, remember, oxygen has 6 electrons in its outer shell. You're going to have one of these, that's 1. Then count all of the double bonds, 2, 4, 7. Have 6 minus 7, which is -1. In the second one, so sulfur is +2, and each of these is -1. For the next one, which is this, again, the sulfur has 6 electrons in its outer shell. So you have this time 1, 2, 3, 5. So this time the formal charge of the sulfur is +5. This oxygen here is 0. which have 6 electrons in the outer shell, and they have 1, 2 for the double bond, and then 1, 2, 3, 4, 5, 6. But these again is -1. Let's work it out over here. So you're going to have so the sulfur again was 6 minus 1, 2, 3, 4, 5. This is +1. In this case, the oxidation state of the sulfur is now 0. 6 electrons. 1, 2, 3, 4, 5, 6. This one is -1. This one is -1. And these two are 0. This time for this sulfur, you're going to have sulfur, which is 6. And then you have 1, 2, 3, 4, 5, 6, 7. That is -1. And this again is -1. And for sulfur here, you're now going to have -2. So the one of the lowest number of different charges is this one here. So this will be the main structure for sulfate, which is shown in this diagram here. And for the sulfur, as we said, 6 electrons. Non-bonding is 0. Bonding is 12 divided by 2. We have 1, 2, 3, 4, 5, 6. Well, 12 electrons altogether divided by 2, which is 0. So therefore, in this case, the charge on this sulfur is 0. Charges on these oxygens here is also 0. And the charges on these ones are -1. And this gives the lowest possible formal charges on the different atoms. So this is the structure of the sulfate ion. Can you work out the structures of these? The Lewis structure has been given for you. So this one has how many electron domains? 1, 2, 3. 3 electron domains around the carbon. 3 bonding, 0 non-bonding. So that's trigonal planar. We can go back to this. It's this shape here. If you have this one, 2 electron domains, 2 bonding, 0 non-bonding. This will give a linear shape. And this one, 4 electron domains, 4 bonding, 0 non-bonding. That's tetrahedral. You work these out, of course, using this table here. So NH3, 4 electron domains, 3 bonding, 1 non-bonding. That's a trigonal pyramid. This has a bent shape, and this one is linear. If you remember, where was it? Well, if you have 2 electron domains, it's linear. This is just 2 electron domains around the carbon. So we draw the Lewis structures for each of the following molecules and critique its shape. We can do that for ourselves. And that will complete this presentation.